In today's presentation, I'm going to be talking about the timing counter. This will be an introduction to the timer counter. Here I show our architecture, and as you can see, the timing counter is part of our layer 2. Now in green are the items that I've already addressed, and yellow is what I'm going to tackle today. So let's start by timing counter capability. So you would use a timer to create delays, to output pulses, PWM type, for event timing, knowing when an event occurs, or for counting the number of events. Also, we're going to use a timer for if we want to have periodic interrupts. So let's talk about specifically about our ATMEGA 328 microcontroller timer. The microcontroller operates with a 16 megahertz crystal clock, meaning it receives 16 million pulses each second. From now on, I would refer to a clock pulse as a tick. The microcontroller has 3 timers: timer 0, timer 1, and timer 2. Timer 0 and timer 2 are both an 8-bit timer, meaning that they can count from 0 to 255. If you need to utilize larger numbers, then we're going to implement something called prescalers. Now, timer 1 is a 16-bit timer, meaning that it can count from 0 to 65,535. Again, if we need larger numbers, then we're going to have to figure out how to implement prescalers. Now, as I noted, the microcontroller can put out pulse width modulation signals. Now, it has capability to put out 2 PMW signals. One is called the OC0A, which is associated with port P6, pin 12. And the other out PWM pulse is called the OC0B, which is associated with port P5, and it would be physically pin 11. Now the timer can also accommodate inputs for counting external events or for generating precise timing based on external signal. The name for this counter is called T0, which is the input. It is associated with port D4, pin 6. Now let's look at the timer counter 1, which is our 16-bit timer counter. So it can output pulses and other custom waveform. These are going to be called the OC1A, OC1B. And these are associated with port PB1 and port PB2, which corresponds to pin 15 and 16. Now for inputs, for counting external events or for generating precise timing based on external signal, the timer counter 1 has the T1 parameter. The T1 parameter is associated with port PD5, pin 11. In addition, it has input capture function, which is ICP1 associated with port pin B0, pin 14. These pins allow the timer to capture the value of a counter at a specific moment when an external event occurs, such as a rising or falling edge of the ICP1 signal. So if you have an external event, the ICP1 will capture that event and will tell you when it occurred. Finally, we have the timer counter 2, which is the other 8-bit counter. This counter can put out an output, which is OC1A. It captures PWM type output, and the OC2A. These are associated with port PD3 and PB3, pin 5, and pin 17. The timer counter 2 doesn't have the capability to read in inputs. So let's figure out how to configure our timer. To configure the timer counter, we need to know two items. The first one, we need to know the value in terms of ticks. For example, for the delay, if we want a 200 milliseconds delay, we need to know how many ticks it takes to represent 200 milliseconds, and that's the number we need to use. Secondly, we need to know how to implement counters for the 8 and 16-bit timer counter, because many times the value of the register is not going to be sufficient for the number we want, for number of ticks, so we're going to have to use prescalers. So let's look at some of the calculations, and that's going to give us a better idea of what I'm talking about. So there are two ways to increment the counter. The counter can be configured to increment by 1 for every tick. Every tick that goes, you increment the timer by 1. Another way to increment the counter, it can be configured to increment by 1 every time the max value of the prescaler is reached. Every time you reach the max value of a prescaler, you increment your counter by 1. Now we also have to know that the available prescaler are 8, 64, 256, and 1024. So in the case of 256, every time we reach 256, then the counter would be increased by 1. Now another piece of information that's going to come handy is that for an 8-bit counter, the maximum count is going to be the 255 times the max scaler, which is going to be 261,120. So this means that the counter is going to count all the way to 261,120 and then roll back to 0. For the 16-bit counter, the maximum value is going to be 65,535 times 2024, which is going to be 67,107,848. Hence, when we reach the 67 million number, the counter would roll to 0. So let's get more specific. Let's calculate the value for a 2 microseconds. How many ticks do we need? How many pulses we need to account for 2 microseconds? Okay, let's calculate the number of ticks for 1 microsecond. So we know that our clock is a 16 megahertz. This means that it generates 16 million ticks in 1 second. This means that it's going to generate 16 ticks per microsecond. So let's go to the next step. Let's calculate the number for 2 microseconds. Okay. So the number of ticks for 2 microseconds is going to equal to 2 times 16 ticks per microsecond. So that's going to be 32 ticks. So if we want to do something every 2 microseconds, that means that we have to do something every 31 ticks. Now, why do I say 31? Because we start our count in 0 and not in 1. So to configure our register, to configure for 2 microseconds, we need 2 pieces of information. The counter's value, which in this case would be 31, and 31 fits in the 255, is under 255, so we do not need, in this case, a prescaler. Now, for configuring our 16-bit timer counter, then this would be the same. The counter would be 31 with no prescaler. So let's do a second example. In this case, we're going to have a 50 microseconds. So as before, let's calculate how many ticks per microseconds. We know we have 16 billion ticks per second, which means we have 16 ticks per microsecond. Let's calculate how many ticks for 50 microseconds. So what we need to do is multiply 50 microseconds by 16 ticks per microsecond, and that gives us a total of, we need 800 ticks. So we need to do anything every 50 microseconds, we need to do it every 800 ticks. Now, for our 8-bit counter, the maximum value is 255, so we are going to have to use prescalers. So this is how we calculate our prescalers. So the first thing we do, we say, okay, we need 800 ticks. So we divide our 800 by 255, which gives us a prescaler of 3.13. Now, the existing prescalers are 8, 64, 256, 1024. So what we need to do is we need to select a number here which is the closest to the one we calculated, but larger, of course. So in this case, we're going to select a prescaler of 8. Now, once we selected the prescaler of 8, then we have to do all the calculations to decide what parameters we're going to use. So the counter value is going to be 800 divided by 8, which is the prescaler we're using, which is going to be 800. So we have a counter value of 100. So the parameters to set up our clocks, so we get the 50 microsecond delay or interrupt or whatever we need, is going to be to configure the counter value to 100 with a prescaler of 8. Now, if we use the 16-bit timer counter, then we can just use the 800 number because it's less than 65,536. So to recap, we first calculated the number of ticks, which was 800, which was greater than our register value, which is 255. So we had to use prescalers. So what we did is we divided our 800 number by 255 and calculated this particular number, which we would use originally as prescaler, but we have a predetermined number that we can use as a prescaler. So we selected the closest, which was the 8. And then we did our calculation again. So we calculated our counter using a prescaler of 8, which was 100. And the parameters that we need to use is a counter of 800 with a prescaler of 8. In the case of the 16-bit, we did not have to do anything because it's less than 65,535. Sorry, so let's do one more calculation. In this case, let's figure what would be the counter value and the prescaler if we need to account for 500 milliseconds. So as before, we calculate how many ticks per for one millisecond. So we have here is 16,000 ticks for 1 millisecond. So let's calculate how many ticks we need for 500 milliseconds. So that would be 500 milliseconds times 16,000 ticks per milliseconds. And the number turns out to be, we need to count 8 million ticks. So now 8 million ticks is way larger than 255, so we need to use a prescaler. So as before, we take our 8 million and divide it by 255, which turns out to be a prescaler of 31,372. So following our process, what we do is we selected the closest to 31,000, which would be 1,024. Then taking the prescalers that we've selected, we do the operation again. So we calculate 8 million divided by 1024 gives us 7,813 as our counter. Now, we also have to remember the max number of counter was 1024 times 255, 261,120, which means that using a counter of 7,813 is okay. So let's see what would be our parameters to configure our clock. So we would need a counter of 7,813 with a prescaler of 1024. Now let's continue our calculation for the 16-bit counter. The 16 counter can hold a counter of 65,535. Therefore, we are going to have to use a prescaler also for the 16-bit timer. So, as before, what we do is we divide 8,000 ticks by 65,535, and that gives us a prescaler 122. Now, we have to select from the existing prescalers, which is the 8, 64, 256, 1024. In our case, the closest to the 122 is going to be 256. So we're going to use a prescaler 256. Now with the 256, we do our calculation one more time. So we calculate 8 million divided by 256. That would be 31,251 to use as a counter. Now this is, yes, I put this number so we remember which is the max value that we can use for the 16-bit counter, which is 67 million. So we are way okay. So the parameter we're going to use to do a 500 millisecond delay, for example, is going to be, the counter value is going to be 31,250 with a prescaler of 256. So that's the conclusion with the example of calculating our prescaler and our counter. So let's talk a little bit about the timer counter modes. So we have a normal mode. In the normal mode, the timer counts from 0 to its maximum value. When it reaches its maximum value, it sets up some kind of a flag or interrupt or whatever we program into it, and then it rolls to 0. So normal mode, it counts to the maximum value and then goes to 0. Now there's another mode is the clear timer on compare match mode. In this mode, the timer counts to a specific value set by the user. That would be the counter that we've been calculating. So the timer counts up to the counter value. Next, when it reaches this value, it resets to 0 and start counting again. So it counts to a predetermined number, and then once it reaches that number, it sets up a interrupt or a flag or whatever we program into it, and then it goes back to 0. Next, we have the pulse width modulation mode. In this case, the timer generates a square wave signal with a specific duty cycle. The duty cycle, which is the percentage of time of the signal is high, can be adjusted. So what you have here is you have a signal that would come on and off at predetermined values, and that's going to be defined again by the counter and scaler that we calculated. Then we have a fast PW mode, similar to the PMW mode, but updates the output faster. And finally, we have the fade correct PW mode. The timer counts up to the maximum value, and then counts down to 0. Basically generates a symmetrical pulse width signal. Now we're going to program all these different modes, and that's when you get a better idea how they work. Well, anyhow, that concludes today's presentation. And we talked about a timer counter. It was an introduction. We talked about the timer capabilities. We mentioned about the pin interfaces. We calculated ticks, which is how we're going to use to program the timers, the counter, and the scalers, basically. And then finally, we talked about the timer counter modes of operation. So anyhow, I hope you've enjoyed this presentation, and next presentation we'll start doing some programming with the counters. Thank you very much.